Welcome! In this video we begin Chapter 3 on functions, and in fact the beginning of Unit 3. In 3.1, Section 3.1, we will cover the first three objectives. Describe a relation. We will see what a relation is. Number 2, determine whether a relation represents a function. And then 3, use function notation and find the value of a function. So we start with a relation. What is a relation? And I'll start with an example. Here is a relation between year and first class stamp price. So look on the left, we see several years, 2015, 2016, 2017, 2018. And on the right, there are some prices of stamps. So in 2015, the price of a first class stamp, follow the arrow, it was 49 cents. Now, in 2016, look what happens. I have two arrows heading out from 2016. One goes to 0.47, the other goes to 0.49. This is because in 2016, for part of the year, the price of a stamp was 47 cents, and also for part of the year, the price of a stamp was 49 cents. And we can do the same kind of analysis looking at 2017, two different stamp prices, and in 2018 it looks like there were two different stamp prices also. So this is the idea behind a relation. It shows how two sets of objects are related to each other. Here is the definition. A relation is a correspondence between two sets. A set X called the domain, and a set Y called the range. In a relation, each element from the domain corresponds to at least one element in the range. Let's take a look at that last sentence and see how that is reflected in the arrow diagram to the left. So the box on the left, that is the domain, and for each element in my domain there are arrows that point away from it, and so that's good. I don't have any number on the left that doesn't have an arrow attached, and that's the meaning of that last sentence. In the relation, each element from the domain corresponds to at least one element in the range. Also, the at least one is kind of important also. It has to go somewhere, but it can go to more than one. In 2015, the 2015 is related to only one price, but for example in 2016 I am associating two different prices, and that's okay. So each element from the domain corresponds to at least one element in the range. The diagram that we saw is called an arrow diagram, but there are other ways of showing a relation. Consider this. This is just a set of points in the plane, but look how the points are arranged. This first point has the ordered pair 2015 and 0.49. I'll say 0.49. That one point kind of gives us this relationship that 2015 goes to the 0.49. Now, let's pick another point in the plane. How about this guy right there at 2016? I'll put a little arrow, so that's 2016 and 0.47. Do you see the arrow that corresponds to? It's that one right there. So every pair, that is an element from my domain and an element from my range, every pair that's connected with an arrow can be represented by a little dot in the XY plane. So that's another way of representing a relation. And a third way that we sometimes see is simply as a set of ordered pairs. It doesn't look quite as pretty. I mean, I like the picture of the points in the plane, and I like the arrow diagram. But yeah, we could also just do a list of ordered pairs. And so for example, this first ordered pair is 2015, 0.49. So there it is in the point. The second is 2016, 0.47. There it is there. And the third one, 2016, 0.49, and so on. So we have three different ways that we commonly use to represent relations. Another example. In this example, the domain is a list of menu items, and the range is a set of prices. And even though I have 1, 2, 3, 4, 5, I have 5 different menu items and 3 different prices. This relation shows the correspondence between an item on McDonald's 1, 2, 3 menu and its price. I give you this example to show you that domains and ranges don't always have to be numbers. You know, typically in our class, yes, they will be numbers, but they don't have to be. They could be lists of menu items too. Alright, here is a relation given just as a set of ordered pairs. So let's draw the arrow diagram and figure out the domain and the range. Alright, well, how about the arrow diagram? 1 goes to 5. Well, maybe, actually, you know what, maybe let's figure out the domain first. The domain and the range. So my domain, 1, 1, 2, 2, 3, 3. So those numbers I circled, those are the first elements in the ordered pairs. Those are going to be the guys that live in my domain, 1, 2, and 3. Now what about the range? So in my other set, the guy on the right here, what is the result of the relation? Where do those arrows go? So the numbers look like 5, 6, 3, 5, 6, 7. So looks like maybe 3, 5, 6, and 7. 3, 5, 6, 7. So the domain is on the left, the range is on the right. Now let's draw the arrows. Okay, the first ordered pair, 1, 5, tells me I have an arrow like that. Then 1, 6, 2, 3, 2, 5, 3, 6, and 3, 7. There we go. So I've made the arrow diagram. The set on the left is my domain, and the set of numbers on the right is my range. Relations versus functions. A function is a special kind of relation. It's a relation that has some really nice properties. In fact, in mathematics, we talk a lot about functions. We don't really talk all that much about relations, to be honest, but the way we start thinking about functions is through the idea of a relation. Okay, so this is really the more important idea. What is a function? So I've shown 3 relations there. It turns out that 2 of these are functions, and 1 of them is not a function. The first relation, that is a function. The second relation, that is a function. The third relation, that is not a function. Can you see what's different about the third one that the other 2 don't have? It's these arrows down at the bottom. It's the fact that I have one element in my domain that is associated with 2 different elements in my range. So one thing in the domain corresponding to 2 things in my range, that prevents it from being a function. Here's our definition. Let x and y be 2 sets. A function from x into y is a relation that associates with each element of x exactly 1 element of y. So notice how in the first case that is satisfied. For each menu item, there's only 1 price that it goes to. The cheeseburger only goes to the 1 price of the $1. The McChicken only goes to the 1 price, that's the $1. Bacon McDouble only goes to 1 price. So it would be a little strange to walk into a McDonald's and you want to order the Bacon McDouble and there are 2 different prices associated with that. That doesn't happen. So we really do have a function. Every menu item is associated with only 1 price. Now, it's okay, don't be confused, but it's okay to have a single price that comes from 2 different menu items. But what's important is that each element of x, these guys on the left, each individual element there has an arrow that goes to only 1 price. The same thing is true in the second example. Every element on the left gets associated with 1 number on the right, but the problem occurs on this rightmost relation with the 240 because 240 is being associated with 2 different numbers. Alright, so a function. That's what makes a function, and how to identify something that's not a function. Well, just like a function can be expressed as an arrow diagram, we can also show a set of points that represents a function. So look at this set of points. It is a relation. I have my my domain. These are all the first elements of the ordered pairs, and my range, which is all the second elements of my ordered pairs. Let's answer some questions. What is the domain of this function? What is the range? And is it really a function? Is each element in the domain associated with exactly one element in the range? All right, so how about the domain? The domain is all the stuff that appears first in those ordered pairs. So the domain is this set: 0, 1, 2, 2.5, 3, 4, and 5. If I were to draw an arrow diagram, those are the numbers that would appear on the left. I might as well do it. I started already. 0, 1, 2, 2.5, 3, 4, 5. And how about the range? The range is going to be all the numbers that appear on the right, sort of the y values of the points. And the range is, well, there it is, all those values. So the range would be, I'm not going to write those out, all those other values there. And one thing you might notice, even just looking at the dots, even just looking at the points on the diagram, is that, yes, it's true, each element in the domain is associated with exactly one element in the range. You know, I don't have a situation like this where there's two dots that are right above each other. That would be a bad situation. If I had two dots that were right above each other, then I'd have one element in my domain, in this case the number 5, getting associated with two different numbers in my range. Okay, but I don't. That never actually happens. I don't ever have two dots above and below each other, directly above and below each other. So this does represent a function. Okay, so the previous slide showed several points and said the existence of those several points makes a function. Look at this. This line represents infinitely many points. There's the point 1, -3 on that line, and there's the point 3, 1. But in fact, there are infinitely many points. There's some point x, y. But all of these points have a particular property. This line is the set of all points x, y, where the y-coordinate looks like twice the x-coordinate minus 5. So, for example, if I look at the 3, 1, I can see that 1 equals 2 times 3 minus 5. The y-coordinate is twice the x-coordinate minus 5. Yep, that's true. 1 equals 6 minus 5. Does the same thing hold here? Is this true that -3 equals, see, I'm not sure, we're just checking it out, 2 times the x-coordinate, 2 times 1 minus 5. Let's see, 2 minus 5 is -3. Yep, that works out all right. So, in fact, every point on here has x and y coordinates that satisfy that relationship, that the y coordinate is twice the x coordinate minus 5. Now what about this? Now a circle is a set of points, and this particular circle is the set of points where the x coordinate and the y coordinate satisfy that x squared plus y squared equals 1. For example, take a look at the 0, 1. The x squared, 0, squared plus 1 squared, oh yeah, that equals 1. And same thing down below, that point down there. 0 squared plus, well, now my y is a -1. -1 squared, oh, that also equals 1. So both of those points satisfy the equation, and they lie on the circle. Now, is the set of points on the circle a function? Is the set of points on the line a function? Well, one of these sets of points is a function and the other isn't. Why not? And maybe you've heard the vertical line test, and that's kind of the reason here. There's no x value that has two different y values associated with it. You know, we usually think of the x on the left and the y on the right from my previous picture in those arrows. So there's no x value that has two different y values. But on the picture to the right, on the circle, I do have an x value with two different y values. There it is. There's 0, -1, and 0, 1. 0, 1, 0, -1. Both of these points are on the circle. But these represent one x value with two different y values. So the circle is not a function, whereas the line is. So I will write yes, function. And the other one is no, not a function. Okay. Let's talk about functional notation. How do we actually write functions out? We often use letters like little f or little g to denote a function. So suppose that f is the function defined by the points in the picture here. We're going to write something like this: f parentheses 0 equals 20. What this means is 0 is an element in my domain, and the number that's associated with it is 20. Like if I drew out my two arrows, I'd have a 0 on the left, I'd have a 20 on the right, and an arrow that points from 0 to 20. Another way of expressing this 0 and 20 relationship is the point 0, 20. And we see that right there on the top left. So now we have three different ways of showing this relationship. I can draw a point that is 0, 20. I can say 0 in my domain is associated with 20 in my range, or I can write f of 0 equals 20. And the f is just a reminder of which function am I currently using. You know, you might have several functions floating around. You want to be sure that you're using the right one. It's also true that f of 1 equals 19.2. Oh, and I've already started using something that we say all the time. It's the of. We say f of 0 equals 20. And f of 1 equals 19.2. So 1 goes to 19.2. And I see that as the point. 1, 19.2. And so on. We do this for all the other numbers until we get to the end. F of 5 equals 0. We have a few ways of describing how the function works that are all the same. One thing I've said is like, you could say f of 3 is 12.8, so there's the point. F of 3 is 12.8. You can also say the function f maps 3 to 12.8. You hear that a lot. One number is mapped to another. 0 is mapped to 20. The function maps 1 to 19.2. Another word that we use often is the image. We say that the image of 3 is 12.8. It's sort of like the function starts off with a 3 and then turns it into something else, and it turns it into a 12.8. The image of 3 is 12.8. And probably most commonly, we just talk about the value of the function. We might say that the value of function f at 3 is 12.8. So get comfortable with this, because all three of these are used quite a bit, and we just use them interchangeably to mean pretty much the same thing. Using this language of image and images is a useful way of expressing the range of a function. So here's the definition for range. We've seen it before, but it's just a new way of saying it. The set of all images of the elements in the domain of f is the range of f. Alright, how about explicitly defined and implicitly defined functions? Here's an example of an explicitly defined function. Consider this equation. In the equation, y equals 2x minus 5, y is explicitly defined as a function of x. And the big key is that y appears by itself on one side of the equation. Y is a function of x. What that means is I can plug in different x values, and when I plug in an x value, it will produce a different y value. If I plug in an x value of 10, then it produces a y value of 15. So it's a little bit like if I had 10 on the left and a 15 on the right, we get something like this. I put in a 10, I get out a 15. If x was 100, then y would be, what is it, 195. All right. So 100 turns into 195. So x is the input and y is the output. Y is a function of x. Now, sometimes the y is buried inside of the equation, and y isn't by itself on one side. Now, if I can solve for y, then we say that y is implicitly defined as a function of x. Now, let's just be sure, can I really solve for y in this equation? Well, let's see, 2y equals 30 minus x, and divide both sides by 2, so y equals 15 minus 1/2 x. Yes, I can get y by itself on one side of the equation, and so yes indeed, in the original equation, y was implicitly defined as a function of x. And I guess at the very end, you could say here, y is explicitly a function of x. Now, if y is a function of x, then x is called the independent variable, and y is the dependent variable. X we think of as the input, maybe input and independent, but x is also independent because it can be anything. In this original equation I said, let x be 10, let x be 100. We could just try lots and lots of different values for x. But y is dependent because once you choose a value of x, the value of y depends on that value. Once I choose 10 for x, y has to be 15. And once I choose a value of 100 for x, y has to be 195. And finally, the independent variable is sometimes called the argument of the function. Functions defined by equations. So let's say I have explicitly f of x equals 2x squared minus 3x. So this tells me how I can put inputs into my function and what the output will be. So f of 5, well, I just substitute the x for 5. So if f of x is 2x squared minus 3x, then f of 5 will be 2 times 5 squared minus 3 times 5. Do you see that? Wherever there was an x originally in the function, now I just replace that with a 5. And we'll work that out. 5 squared is 25, so twice that is 50. And I end up with 50 minus 15, and the answer is 35. So f of 5 equals 35. If I had an arrow diagram, then for my function f, I'd have a 5 on the left and a 35 on the right, and arrows that go from one place to another. And if I was plotting this function out as a bunch of points, I might have 5 on my x-axis and 35 on my y-axis, and I'd have a point right at 535. What's the value of f of x plus f of 2? Well, the f of x is easy. I'll just repeat what I see up on top. 2x squared minus 3x plus, oh, now I need f of 2. All right, let's put f of 2. So I'm putting 2 in place of x. 2 times 2 squared minus 3 times 2. All right, so that's 2x squared minus 3x plus, and if I simplify all that, let's see, 8 minus 6, looks like it's 2. Now what about this, 3f of 5? Well, that's just 3 times f of 5. Well, I'll make it explicit. 3 times, well, maybe I shouldn't use an x for times since I have an x floating around. 3 times f of 5. f of 5 we figured out earlier. f of 5 is 35. So that's 3 times 35, which is 105. Look at this last line. This is where things get a little tricky. If they weren't tricky already, they're getting tricky now. f of negative x. All right. So in my definition of the function, f of x equals 2x squared minus 3x. What that means is f of anything equals 2 times that thing squared minus 3 times that thing. So in place of x, I am going to put negative x. So I get 2 times negative x squared minus 3 times negative x. So just like I replaced the x with 5 when I wanted to figure out the first line, Now I'm replacing x with negative x to figure out the last line. All right, well, negative times a negative is positive, so negative x squared is simply x squared, so that's good. Now what do I have? Minus 3 times negative x. Well, 3 times negative x is, I guess, a negative 3x, so I'm minus a negative 3x. So I can write this as 2x squared plus 3x. All right, the last few calculations. What if I have a negative in front of the whole x? Well, then I just put negative in front of my whole function, 2x squared minus 3x, like that. So I get negative 2x squared plus 3x. Do you remember how you distribute that negative sign across a sum or a difference? F of 3x. Well, now I'll just replace my x with 3x wherever I see it. 2 times 3x squared minus 3 times 3x. And let's go ahead and simplify that thing. What do we get? So 3x squared becomes 9x squared. You can think to yourself, like 3x times 3x equals 9x squared. So 2 times 9x squared minus 9x. So 2 times 9 is 18. Looks like we get 18x squared minus 9x. F of x plus 3. So let's just replace the x with x plus 3. Now you really have to be careful, because I'll write something that's wrong, and you tell me why it's wrong. So I want to replace the x with x plus 3, so 2x plus 3 squared minus 3x plus 3. Right, do you see what's wrong? The way I've written it out, it looks like I need to square the 3, and then I'm adding that to 2x, but this x plus 3 is like, it's like a quantity that has to be maintained together. So wherever it appears in the function, I have to put parentheses around it. In my original function, the x was being squared. So if I replace the x with something else, that something else has to be squared. And in the original function, x was being multiplied by 3. So if I replace that x with something else, that whole something else has to be multiplied by 3. Just as an option, I will go ahead and expand this out. I'll do it quickly, and you can pause the video to check it and see if you understand it. I'll go to the right first. So I will expand the square, get x squared plus, I know I'm doing some shortcuts here, minus 3x minus 9. Distribute the 2, 2x squared plus 12x plus 18 minus 3x minus 9 equals now 2x squared. Now I can combine my x terms. I have a 12x and a minus 3x, so that gives me plus 9x. And I have just numbers. I have a plus 18 and a minus 9, which gives me plus 9. All right, here we are. We've made it to the very end. Our last problem, f of x plus h. You know what? Let's just take it a little bit easy on this problem. Let's just call this 2 times x plus h squared minus 3 times x plus h. Don't forget, keep that x plus h in parentheses. And if you really want to, you can expand it out, but I'll leave that for you. This looks like a good place to end the video and to end our introduction to functions. Functions are powerful. They show how an input and an output are related, and we'll spend a lot of time talking about functions. In fact, it's fair to say that I don't know, 95% of all mathematics is about functions and using functions as a tool to gain deeper mathematical understanding. All right, that's it for this introduction.